So this talk is about DynamoDB. I'm going to start with this one, which is probably a better talk. It's like, you guys didn't want to give me a round of applause? Come on, start. Okay. I did not expect this slide here. Do you have any idea what the slide is about? I put this slide. Okay, so this is probably an indication for you how the rest of this talk is going to go. Craig and I worked together for several years. My name's Amrit. I'm the guy on the right here. We worked together for several years, but we go back and forth a heck of a lot. That's what you're going to see during this talk. Both of us work on DynamoDB. He's Craig, I'm Amrit. What I've found in the last 6 or so years that I've worked in DynamoDB in AWS is that customers who build applications on DynamoDB need to understand not only how the service works, but also how we made some of the decisions about how the service works. So this talk is more about how we made those decisions. This is who we are. The exact decisions we made may not be relevant to you, but what I hope you will take away from this is how we come about those decisions, because those may be more applicable to you as well. So the way in which, as a large organization making a service like Dynamo, I think somebody here is wondering which talk they're in. This is the DynamoDB talk. Okay. The objective is, if you have a large team and you need to make everybody in the team able to be productive at their maximum level, you cannot have centralized decision making. We build a distributed database. The idea is you want to distribute things across many nodes and have the power of many nodes. What's the point in having a team which has one decision maker? No point. So we have tenets in DynamoDB, and these give the team an understanding, a shared understanding, so that we can push down decision making into the organization. This is something which I think you should understand. This is how we work at Amazon. This is something which is common to all AWS services. It helps teams make decisions, and these are our tenets. First, security. Second, durability. Third, availability. These are non-negotiable. I don't care what the feature or the implementation choice is. I will never trade security in order to give you something else. And what's the fourth one down there? Predictable low latency. This is a DynamoDB feature. We want to guarantee predictable low latency at any scale, but we will never trade one of those. So in the rest of this talk, what you're going to hear is a reiteration of these tenets: security, durability, availability, and predictable low latency. These need not be the tenets in your organization. But as a decision maker in your organization, the thing I would urge you to do is think about what these tenets are. Make sure that everybody in the team has a shared understanding of these tenets, so that when they're making a decision, they will understand what these tenets are. Now, in the rest of this talk, we're going to talk about these over and over again, but many of these choices are going to come down to predictable low latency, because like I said, security, durability, and availability are non-negotiable items. So if we have to give you predictable low latency, just show of hands, how many of you here use DynamoDB, and how many of you have never used DynamoDB? Never used DynamoDB, show of hands. All right, very small number. The rest of you understand, we try to give you predictable single-digit millisecond latency at any scale. So with that, let's talk about...
All right. You've talked enough.
All right, this is how it usually works with Craig. You want to take it over? Yeah, go ahead.
Yeah. So we're talking about scaling, right? And I want to give you a sense of the scale of DynamoDB. 500,000 requests per second, right? That's a lot, right? We have hundreds of tables right now, just right now, that are all pushing 500,000 requests per second. This is just normal for us. Every day, this is what we see. And it's not just, just barely 500,000. We've got, for instance, the Amazon stores business. On Prime Day, they peaked at 151 million requests per second. That's one customer of ours. So a lot of the scaling causes us to think about things a little bit differently. When you combine the scale with state in a distributed system, this is where a lot of the challenges come from. I'm not saying that stateless distributed systems are easy by any means, but stateful is a whole nother level of complexity. Before we get into a lot of the details of Dynamo and some of the specific choices that we made, I want to talk about some of this problem in the abstract, just kind of so we're all on the same page. So if you're building an application that has state, the simplest thing to do is put the application and the state on the same instance, right?
Sorry, are you saying that it's going to be easy to do this, or is this easy, or what?
Concurrent programming is not necessarily easy, but relatively speaking, yes, I'm saying this is easier than distributed state management. This pattern works great for a lot of applications, but pretty soon you want to scale things independently. And so you move your state onto a separate instance. And now you've got to deal with failure, right? Because you've got these two things now that have to be available. Your application server has to be available, and now your stateful server has to be available. They both have to be available, so this is strictly less available than the previous approach. But you get some benefits because you can now scale the state and the application independently. But it also means that the state can disappear out from underneath you at any time, and so you have to think about these failure cases throughout your code everywhere.
So how does your application actually know what the state of the underlying database is?
Well, in some cases it doesn't, right? Because especially as we start scaling, we get to the world where we say, hey, one instance isn't sufficient. We're going to have multiple instances, and now we're introducing coordination, and coordination is where a lot of this complexity comes from, right? And so you can end up, one of the simplest things you can do then is move from a single instance model to a primary and secondary model, right? And this is great. You do all your reads and writes to the primary, and you think through this, and you're like, okay, well, I got to deal with when the primary fails, right? That's easy. Everybody thinks about what happens when the primary fails.
What happens to the other side? Secondary fails.
Oh, the secondary fails. Yes, this one's actually more interesting, and this is one it's a little more subtle, is because what do you do in this case? Right? Do you continue to accept writes on the primary? But those writes won't end up on the secondary because it's down. And so what happens to those writes? When the secondary gets healthy again, how are you going to repair all this? And you start getting into a lot of these corner cases and the complexity that comes from the distributed state coordination. Right? And so 2, right? Well, maybe 2 isn't the answer. So 3. 2 doesn't work, let's try 3. We'll just keep counting up here. So 3 is the real minimum then, right? Right? Well, this is great, because now if you want to survive a single box failing, you can, because you've still got 2 healthy, and you've got another one, the write comes into one of the nodes, and you can get it to one of the other nodes. So now your write's in 2 places, and that write is no longer susceptible to losing a single box.
If 3 is not enough, what are you going to do?
Well, so 3 is not enough. Let's try 4, right? If 3 is good, 4 must be better. Okay? Well, so with 4, now in theory you can survive 2 failures, right? Because I can still get the write to the other node, and that's fine. But, how
do you know these 2 are the correct 2?
Okay, how do I know that? Yeah, so there's this failure case, right? Maybe all the nodes are actually healthy, and they just can't talk to each other. We have a network partition, right? So both sides think that, well, I'm on the healthy side, the other side's dead, I'm going to keep accepting writes. And so you end up with this what we call split brain, where you've got writes, the data set diverges over time, and now when this partition heals, you've got these 2 totally different data sets you have to merge. So having an even number is a horrible idea. 4 is a really bad option.
So basically the idea is you need to have an odd number of nodes? Is that the story?
Yeah. So what about 5? Let's keep counting up, right? So 4 is out, we could do 5. So with 5, you can survive 2 failures. Maybe that's good, maybe that's what you want. But what we've found through a lot of our experience is that as soon as 1 fails, you're working as hard as you can to get that replica back to par. You're bringing in a new node. You're going to repair the situation. And so what you're actually doing here for the second failure is you're racing how fast can I get a node healthy again to get this cluster back to par, back to normal, before we lose another box. And so a lot of the effort that goes into having more nodes might actually be better spent trying to repair a node faster, because you're going to need to do the repair in this case anyways.
So at this point, you're basically saying you need to have an odd number of nodes. Is that it's like 3 is okay, 5 is okay, 4 is not okay, 2 is clearly not okay. Is that?
Yeah, right. And you know, as you're going up, you have to do more writes. Like even in this world, like you have to have the majority healthy so that you know that you're on the healthy side. And so you're adding more boxes, and so you got to think about the cost. So let's take this to the extreme. Like let's say for scale reasons you need to have 1,000, 1,001, because it's got to be an odd number, right? So I got 1,001. In order to accept the write, I've got to have 502 boxes. Yeah. It's got to be the majority. Accept the write.
Well, statistically, you can't do that. No.
Oh, okay.
Because any one of those 500 and whatever boxes can fail. So if you do this, you're going to trade off availability.
Yes. It's also really expensive. Because you just, like, you've got all these, like, you really need to write that thing 502 times just so you know you can survive some failures? Yeah.
So what do you do?
So an alternative that we think is a much better alternative is you have lots of groups of 3. You still can have, 1,000 nodes or however many tens of thousands of nodes, wherever you want, but you group the data sets into groups of 3. Because in the groups of 3, it has all the properties we like, right? We can replace the boxes quickly. We know it's correct. It's a nice odd number.
How do you know where to send a request to?
You and your complexity. Yeah. If I send a request, I want to put all these boxes behind a load balancer, right? So the client doesn't necessarily know. In this case, C, F, and J are the 3 boxes that are in the cluster for the data set that this client is interested in. But if I send a request through a load balancer or whatever, it's probably going to land somewhere else. Almost certainly as the number of boxes goes up. And so what K has to do then is like, okay, well, K can either return a redirect or it can proxy onto the correct node for you. But if you think about that, right, K then just becomes the client because K's got to know the data set. And so we have the exact same problem to go solve of, for this particular data set, where is it? I got a lot of boxes.
So basically you're going to add one level of indirection here and say that every problem in computer science can be solved with one level of indirection, and K needs to know where to go look this up. Okay, fine, all right.
Yeah.
Okay, that thing,
okay.
right.
Have you seen these slides before?
No,
yes.
I have not. You made the slides. I haven't seen them.
Okay, I made the.
No.
So, yes, another level of indirection, right? And so we add a data set, which is the data about where the data lives, so our metadata, right? And so the protocol then is the client, in order to go figure out, I want to go talk, get this particular data, I do a lookup in metadata, and then I go get the box that I need to go connect to, right?
2 lookups is like expensive.
Yeah. So now we're doing double the lookups. And so if I have to do X requests per second to the data set, I also have to do X requests per second to the metadata set. So I know what you're going to suggest next.
Yeah. There has to be an easier solution, because if you were to do this, then you need to scale your metadata to the same capacity as your actual data, which I'm not willing to do. So
yeah.
You need to give me a different answer.
So we've got 2 of our classic computer science solutions now, an extra layer of indirection and caching. Right? So if you add a cache here between the metadata, which is fine because these data sets don't change that often, you can cache this. You have less than X requests per second, and metadata doesn't have to scale to the same request rate. Any snarky comments about this one?
No. Okay. What are you going to do if your caches are cold, and what are you going to do in situations where your metadata is not able to keep up with the uncached data? All of those things.
You are foreshadowing your portion of the presentation that's coming up later.
Thank you for telling me what I'm going to talk about. It's going to be nice to know.
So caches can be a risk, and we'll talk about that more later. We'll also talk about how we do this routing in a little more detail. The other thing is boxes can still fail. Right? So we have these large boxes. We have to deal with this case. And so when a box fails, and so in this case, J has failed, and we want to replace it with L then has to then go and update metadata somehow. and indicate, hey, I'm part of this set, right? And so we have this problem, right? This problem is, who is the authority of which servers participate in which groups, right? You think it should be the metadata because where I'm doing all the lookups. But we've got this race between when a box becomes part of one of these clusters of 3 and when it can serve traffic and when it tells metadata and when the client caches can recognize it. We're going to talk a little bit more about this as well.
So basically the idea you're talking about is a system which is a system of record authority and something which points to it which is potentially eventually consistent. So are you suggesting that for scale you need to understand eventual consistency and deal with it?
Yeah. Yes.
Okay.
It's hard, but
all right.
It's hard, but that's reality,
works for me.
Right?
Okay.
But of course, we've got this magic metadata thing we've been talking about. What the heck is this? Like, how's that going to work? There's two options here. Like, we could just make metadata another one of these tables, right? And this works great. Like, but you still have that routing problem of which subset of metadata do I need to talk to? And so I got to go solve all of that again. It makes the writes relatively simple though, because there's only one place I need to write to, and this system's going to have a lot lower request rates because of the caches, but it's also going to be significantly smaller because all you need is a single item to say, hey, like tens of gigabytes of data that you're looking for, they're over there. And so this system's going to be multiple orders of magnitude smaller in terms of data size as well, which opens up an alternative of, instead of having subsets of this, you can have entire replicas, right? If you have entire replicas, the lookup problem gets really easy because as a client, you have to talk to one of the metadata nodes. It doesn't matter which one. But the trade-off is it makes the write problem a lot harder. When we change the membership set, somehow we now have to go update all of the metadata nodes that exist because you can't predict which one the client's going to go talk to later. So this makes it more eventually consistent. Oh, that was the back button.
Way. All right.
I apologize. There we go. So through the rest of the talk, we're gonna dig into 3 aspects of this and choices we've made in Dynamo, and look at it kind of a more tangible of how did Dynamo decide to solve some of these problems. We're gonna look at request routing, how does the client get to the storage that we just described. We'll talk about how we structure our metadata. But also in a system this size, we'll talk about some of the constraints and the limits that we have to put into place and why those exist. As customers will run into these, and if you understand why, we think this will help you build your applications. So routing. Very simple description. This is what Dynamo looks like. Storage node fleet on the right is what we were just talking about, with that large, thousands of nodes with clusters of 3, and the request router fleet is the fleet that sends the request to the appropriate box. And so when a client comes in, they get sent to a random request router node. Okay? And the request router has 2 jobs. The first one is to do authorization and authentication. Are you who you say you are? Do you have access to this data? This is where we do the SIG-v4 processing. Then we also do the metadata lookup. And from there, we say, okay, now I know which particular storage node to talk to. We forward the request on. Okay. This picture's too simple. There's more to it, right? I said load balancers. So we've got load balancers in front of the request routers, and they're just normal load balancers. We use network load balancer. But because we have so many load balancers, we have DNS in front of the load balancers because it becomes like the load balancer of the load balancers, because it's the thing that sends traffic to all the load balancers. And of course, we're running within a region. Regions have availability zones. Availability zones are independent failure domains. An availability zone is composed of multiple buildings where the actual EC2 instances eventually run. At the end of the day, we're all talking about like there's real hardware somewhere. So this separation is really important for how we provide our availability, durability guarantees, but it provides some challenges for latency. So that's what we're going to talk about. So everything we have is just an EC2 instance at the end of the day, which means it runs in an availability zone. we've been very careful about how we've put our servers across the availability zone, right? So we've striped them across multiple availability zones. And every availability zone, we have a choice here. We've constrained our load balancers to be within an availability zone because we find it easier to think about these units of failure. This is the choice that we've made, and this picture is overly simplified. If you zoom in on one availability zone, I think I double-clicked on that one. I did double-click on that.
Yeah.
If you zoom in on one availability zone, we've got a whole bunch of load balancers, and behind every load balancer is a bunch of instances, but I'm simplifying the picture. So if we go back to the simple picture, like load balancers there, every Dynamo table is divided up into partitions, which we'll talk a little bit more about later. Every partition has 3 replicas. And so we've spread the replicas across the 3 availability zones. Right? And this is how we provide our availability and durability guarantees. Right? Because as we talked about at the beginning, we can lose one box, one replica, and this cluster can stay healthy. Right? Our risk is if we lose 2. And so as soon as we lose 1, we're going to try very hard to replace this, and so we're trying to replace the instance as fast as possible. But our risk is correlated failure. And the most likely correlated failure we'll see is across an availability zone because of some larger scale events, because we do all of our software deployments, we scope them all to an individual availability zone. We want to make sure if 2 boxes fail, they don't impact 2 of the replicas in a partition. We do this by spreading them across availability zones. So this is critical to what we do. But there's a consequence to this, right? These availability zones, like I say, they're physical buildings, they're connected, and you can and you should do this, is look at the distance between some of these, the network distance I'm talking about. Launch 2 instances in an availability zone, ping them, see what times you get. Do this in different availability zones, you'll see it's different in different availability zones. Do the same thing across availability zones. You'll see it's different across availability zones. What's always true is that the network distance between availability zones is significantly higher than the network distance within an availability zone. And so our clients are running on EC2 instances, Lambda functions, containers within ECS, EKS, whatever it is. They're in availability zones too. And so the simplest thing we can do for load balancing is to randomly route across all of our available instances, which means we're highly likely to route a customer across an availability zone and back across an availability zone. So we'll be paying the extra latency penalty multiple times. So ideally what we'd like to do is this, and use the shorter network path. And this is meaningful to a service like Dynamo, because if you look at the components of our latency, our server-side processing time is actually relatively small and of a similar order of magnitude to the network distance itself. And so one of the biggest things we can do as we work on improving our predictable low latency over time is shrink the distance. We don't have to do any software optimizations within the server itself. We just shrink the distance. And by shrinking the distance, that ends up with a meaningful improvement in customer latency. So I said DNS is our load balancer across load balancers. So if you do a DNS lookup for our domain name, this is US West 2. You keep doing this over and over again, you'll get different IPs for different load balancers within the regions. So one of the things that we can do then is we can do split horizon DNS, is where you get a different answer depending on where the query came from. And so if you're in one of the availability zones, you'll get a set of load balancers in that same availability zone. If you're in a different availability zone, you get load balancers from there. And so that means that DNS is our availability zone selector as well. Okay? And that's it, piece of cake, right? We're all done, woohoo! Mm-hmm. Well, failure is where this all gets hard, right? This is what we expect to see, this is what we like to see, is you end up with a third of the traffic in every availability zone, meaning every availability zone processes a third of the requests. That's relatively easy to scale and deal with from a capacity planning perspective. We got to deal with a case where an entire availability zone fails, or we want to take it out for whatever reason. In that case, what we then have to do is all the traffic from that availability zone now has to go somewhere, because we prioritize the availability over the latency, right? And so you'll notice here that availability zone 1 and 3 are now seeing a 50% increase in the amount of traffic they would have had otherwise. And so as a regional service, this is a thing that we have to plan for ahead of time. And so we just have capacity sitting there ready all the time. This is the price of doing business as a regional service, and AWS services, price follows cost, and so this is baked into the price of DynamoDB. To be able to handle things like this so customers don't have to know under the covers that, okay, we're dealing with an impaired AZ at the moment. So that's fine. But if you think about the case like, well, what if the traffic in one availability zone is significantly larger? We have a traffic skew. Well, one option is we could just scale up the number of servers in that availability zone. That's relatively easy, right? But again, think about what happens when that one fails. Now what you see is availability zones 1 and 3, they have to handle a doubling in traffic. So that idle capacity that we have to have sitting there ready in case of this event is significantly larger. So this is a way more expensive way for us to run this service. So that would mean that we'd have to pass on the cost to customers, and so we don't like that option. The alternative is what we do is we say, well, we'll never send more than a third of traffic. This makes our DNS management a lot more complex, and it does mean that some requests will always be going cross availability zone. In reality, law of large numbers helps us out, and we don't have a very large skew, and so we don't really see this scenario. We also have some traffic coming straight from the internet, and so the internet is close to every availability zone at the same time, and so we can send that traffic wherever we want with more DNS complexity, so we can fill in the gaps. But these are the types of things you must think through as you're building this style of architecture. But that's how we shrink the first hop. This is a big latency win, but there's more, right? Because you look about that second hop between the request router and the storage node. Again, ideally we send a third of the traffic everywhere. From capacity planning perspective, this is easiest. Dynamo did this since launch, and the thing is we've kind of baked in this model into our capacity planning, our pricing, and our limits. Because when you're doing a strongly consistent read, you must talk to a node that we've elected leader. So there's only one box you can talk to. You have the request processing capacity of one box. But eventually consistent reads, you can talk to any of them. And so we said, okay, well, one of the boxes might be unhealthy, so we can't count on that. But we've got the processing capacity of 2 boxes. That box has to be there anyways, so let's just use it. So this is why in eventually consistent reads, the limits are higher and the price is lower. It's because we have this capacity that would have been idle otherwise that we can use all the time. Actually making this change to route locally is pretty easy because in this case, we control the client and the server. We have to know about all 3 replicas anyways. And so we just pick the one in the same availability zone that we are. We send all the traffic there. Unless, of course, you're relying on this fact that you can send 2x the request for an eventually consistent read, because you could now be sending 2 boxes worth of traffic to a single box. That's no good. And so what we have to do is we actually have to monitor statistics on the server side and detect when this happens. This happens sometimes, doesn't happen super frequently, but when it does, we can send a message back to the client and say, hey, for this table, let's go back to the random routing mode because we need to prioritize availability over the lower latency in this case. And again, in reality, most of the tables that are much higher traffic, their clients are distributed across availability zones all the time, and so they're being routed to each individual availability zone, which means that when we do the local AZ, we see the spread that we'd expect to see, and so we don't end up in this case as often as you might expect. So this is the path that we've taken on how we can shrink our latency, and a few times we've bumped up against this, the availability versus predictable low latency trade-off. And when forced to choose, we're going to make the service available. But in a lot of cases, there is no conflict, and we can do both. It leads to a bunch of complexity on our side, but these are the tenets and the most important things for our service and for our customers. And so we think this complexity is worth it in order to provide a better product to you folks.
I know the next slide is, do you want me to take this one?
Yeah, I hope so.
Okay, all right. Get a drink of water or whatever you want. So a couple of things which Craig mentioned. He talked about how we do client routing, and 1/3 of the traffic goes to each AZ. Another thing which we do is we try and keep 1/3 of the leaders on each AZ. Therefore, even on the strongly consistent reads, you're evenly distributing traffic across the ACs. Sorry, didn't want to interrupt you when you were talking about it.
That's a first.
All right, first time I'm seeing these slides, so it's going to be interesting. All right, so you have a request, it comes in. You talked about how it goes all the way through to the request router. The important decision which a request router needs to make is, should we serve this request? And should we serve this request is a three-part question. Are you who you claim you are? Is your SIG-V4 signature matching your request? Do you have the permission to do the thing which you want to do on the table which you're claiming you want to do it on? And the third one is, are you within your limits? So those are the three questions which we have to answer each and every request we get. Now, we've got hundreds of customers who do over 500,000 requests per second. We do this stuff billions of times a day. And we have to do this really, really fast because what are we after? Predictable low latency at any scale. That's what we're supposed to get. Okay.
Okay.
All right. I don't know about this crew, but okay. All right. Thank you. Somebody heard it. So we're after predictable low latency, but once the request router knows that your request is legitimate and we do want to serve it, the next question which we have to ask is, which storage node do we send it to? Now, Craig talked about distributing a table into multiple partitions and partitions across multiple storage nodes. We have 3 storage nodes here. Sorry, I don't have a clicker here. But there's literally hundreds of thousands of storage nodes across which we distribute data. When I asked earlier, how many of you use DynamoDB, or how many of you don't use DynamoDB at this point, only one person raised their hands. So the rest of you, I have a simple ask of you. Look to your right, other right. Okay, look to your left. All of you who use DynamoDB, your data is co-located on storage nodes with people who are next to you. It's completely shared infrastructure. We do not spin up a cluster for you. So your data is co-located on hundreds of thousands of storage nodes with other people's data. And hundreds of millions of times a second, we need to decide where to send each of these requests. So that's the problem which we have to solve. Once the request makes it to a storage node, first, all data is always encrypted at rest. Anybody know why? Shout it out if you know why. What's the first tenet I talked about? Come on, shout it out. I can't hear. I don't have. Security. Thank you. Security. All data is always encrypted at rest. You can provide us a key, but if you don't provide a key, one will be provided for you. All data is always encrypted at rest. So we need to get that security, that key. Then we need to decide, are you overrunning a partition? Shared infrastructure, rate limits, provision throughput, all of those kinds of things. We need to make sure that we want to admit the request. So there's 2 places where we decide whether to admit your request or to throttle you. Once we're done with that, we have to serve your request, and your response is going to go from the storage node back to the request router and back to you. Everybody good with this flow so far? Quick show of hands, yes or no? All right, more than 50%, okay. For those of you who used DynamoDB before, simple table, unique attribute, login name, non-unique attribute, human being's name. So somewhere in the middle there, there's 2 people with the same name, but they have different login IDs. You've all faced this problem. The primary key on this table is the login. So when you create a table, we ask you for 3 things, only 3 things. What's the name of the table? What's the primary key? What's your credit card number? Only 3 things. How are you going to pay for it? That's your primary key. Once you tell us what the primary key is, we compute a hash of your primary key. We order your data based on the hash. Notice that the order of the names is different from the order of the names on the left because we ordered it by hashes here. Contiguous ranges of hashes become partitions. Craig talked about partitioning a table for horizontal scale. This is partitioning for you. Once you've partitioned the table, if you want to fetch an item, I need to find the partition where it is. So I want to find the item for Jorge or for Richard or whoever. I will compute the hash on that. I will find which range of hashes it falls within, and I will send my request to that location. Hundreds of millions of times a second with predictable latency. That's the thing we're after. So in matter of fact, we've built a system which will do this in tens of microseconds, literally. We measure this thing, and when it starts to get out of this bound, we're really antsy about it because we do it so often. And what we have to do is locate the partition where your data is. You all right? All right. Locate where your data is, and today the traffic we have is hundreds of millions of requests per second. But at any point in time, the things which we have to deal with are, how many storage nodes do we have? How many request routers do we have? All these numbers are measured in like 6 digits or more. And at any point in time, you're creating tables, you're dropping tables, you're scaling up traffic on some table. We're splitting a table because of that. Partitions are moving around, and we need to figure out where your data is in tens of milliseconds. Tens of microseconds. So I want to talk to you about how we go about doing this. And I want to reiterate, effectively what I want to get back to is the point which Craig talked about, which is state is hard, shared state is really hard. This is a distributed system we're trying to build where these things on the left here, I really should get a laser pointer, but these request routers on the left here need to be able to figure out in tens of microseconds which storage node your data is on, because those storage nodes at the back there, they're doing 3 cards, shuffling all the time. They're moving partitions around, they're splitting partitions, changing key ranges. You're dropping tables, creating new tables. These things have to stay in sync. All right, this is the problem we have to solve. So how do we go about solving it? These are the piece parts which we have to deal with. There's request routers, there's storage nodes, there's a control plane, create table, update table, drop table, delete table, and there's this thing which you introduced called metadata, partition metadata, which we're supposed to go look up. These are the piece parts. So let's talk about this situation. You create a table, you update a table, do a synchronous update to partition metadata. Yeah, this is scalable. How often does this happen? Relatively low volume, tens of thousands of times a second. Not a problem. We can deal with this. Partitions moving around, partitions splitting, leadership moving around on storage nodes because we're doing software deployment, hundreds of thousands of times a second. If you're going to start updating your partition metadata, you're building a pretty serious database in the middle there. That in itself will become a scalability problem for you. The worst situation you have is you, our customers, sending us billions of requests, each of which need a lookup of metadata. So effectively, this metadata system is going to have to handle the same front door traffic which DynamoDB handles. This is not a scalable system. So let's look maybe at the next obvious choice. Any snarky comments from you? Okay, all right. First option, put a cache here. How many of you have been in a situation where you're building a system and somebody in your team says, I need to scale, I'm going to put a cache in there? How often has it worked out well for you? Caches are a great solution. They are a dangerous solution. And we'll talk about why. Great, so I have a cache. Every request router now has a cache. Magically, we've implemented one. The size of the arrows from the request router to the partition metadata went down. Let's assume this cache has a 99% hit rate, okay? Partition metadata is serving only 1% of the front door traffic. Cache misses. Any idea what could go wrong in this system? Shout it out if you can. I can hear you, even if you have headphones on. Stale, all right. What happens if all your caches go stale? If one cache goes stale, yeah, who cares? What happens if you have a situation where, for whatever reason, hundreds of thousands of caches go stale? Now your partition metadata is going to get hundreds of thousands of cache misses, and it's going to fall over. We thought about this and said, yeah, the system, yeah, maybe not. So we went one step further, and we also said, this is a situation of a large fleet and a small fleet, a large fleet of request routers, and a small fleet in partition metadata could cause the small fleet to fall over. One of the things I said when I started was the specific choices we made may not be relevant to you, but there are some concepts which you should take away. If you're ever building a cache and a large fleet drives a small fleet, be very careful, because it's not going to end well for somebody. All right, so this didn't work. So we came up with a next generation system where we built a 2-tier cache, where we said memds is going to be one tier of cache, and the request routers are going to have another tier of cache. One tier of cache is eventual consistency. This is now eventual consistency on top of eventual consistency. So keep that in mind when I say this. You create a table, we're going to push it down to memds, great. There's going to be a poller there which is going to go read all the storage nodes and say, what partitions do you have for what tables? Great, I'll push it to memds, great. This is now, memds is now an eventually consistent cache. You make a request on the request router. If it gets a cache miss, it goes to memds, which is itself an eventually consistent cache. This is the system we built, and let me tell you why I think this works. Control plane, push, new table creation, great. The one thing which we added here is we versioned the data across the board. Whenever there's new data in the place of it, you talked about place of authority, right? Yes. The authority is the storage nodes. The storage nodes know what data they are. You're a storage node. Do you know what partitions you have? Absolutely you do. So if the partition publisher comes to you and asks you, what partitions do you have? You will give an absolutely authoritative answer. That's now pushed to memds. But that is the state at that point in time. But you also say, my version is now version 20 or something like that. At some point, if you want to move a partition from one place to another, or there's a split, it comes to the same thing. Bump the version number. So here's what we did. A storage node had version 20 of metadata. It split a partition, it moved a partition. The new storage node says, I'm now at version 21. Now, if a request were to come in to the front door, the storage node says, I have a cached value which says 20. Maybe it had a cache miss and it went to memds and memds said value of 20. Doesn't matter. It goes to the place where version 20 pointed it to. Version 20 is the authoritative source, and it says, not going to work. You actually need to go to this other place because now we're at 21. The immediate thing which we do is the request is going to go straight to the new place, and it is going to get served immediately. So even if you have eventually consistent data in this system, like the caches are 2 tiers deep and eventually consistent, if you do have a cache miss, which happens infrequently because there's a partition split or a partition move, we are still able to serve that in reasonable time. If you're interested in how all of this stuff's supposed to work, we published a paper about this. That's a QR code, scan it. Actually, this is not being recorded, so you probably want to scan it. Or if you want to, contact me afterwards. The basic idea is this. You've got a system with data which has entropy. You have a need to do stuff with caches, and these caches are going to be eventually consistent, and they need to deal with the situation where all the caches can probably go cold. So far, I've talked about the first two. I haven't talked about the last one, so let's talk about that one. System of record, authoritative there, 2 levels of eventually consistent caches. We're good so far. Now let's talk about the situation with large fleet, small fleet, and hedging. If you're ever building a system and you want predictable latency, use this concept called hedging. We do it internally. when a request arrives, and by the way, hedging is not our idea, it's an idea from Google, that's a copy of the paper up there. When a request shows up at a request router, in the eventuality that we have a miss on the cache, we don't make one request, we make two requests to two MemDS servers. Why is this a good idea? Assume that your system is like most systems and your latency is along some kind of normal distribution. If you make two requests, statistically, one's on the left of the median, one's on the right of the median. Take the first response. It's always good. We hedge our requests. What this means is that in the eventuality of a cache miss so far, MemDS is serving twice the traffic which we're getting for cache miss. We go one step further. What happens if all the caches happen to be cold? We introduce this concept of constant work. You make a request to DynamoDB. That request goes through load balancers and all of that stuff, shows up at a request router. The request router says, where's this item? The cache is correct. It makes a request to the storage node. The storage node serves a response. We've already given you the answer. What do we do in the background? We send two requests to two MemDS servers, even on a cache hit. Everybody with me? On a cache hit, we send two requests to two MemDS servers. Why? Assume someday all the caches went cold. MemDS would not know the difference. Large fleet, small fleet. This is the cost to us of doing business and giving you predictable low latency at any scale. These are the things which we keep in mind when we build our systems. And we try to build systems with a guarantee of availability. We can't just say your cache is cold, therefore we had loss of availability. Can't do that. The latency needs to be not just low, but predictably low. These are some of the considerations which we had to go through because these were our tenets. Figure out what your tenets are and have your decisions mirror your tenets. You're not going to probably have to make the same choices, but in the event that you do, my suggestion to you is be very, very careful of the person who says, we'll add a cache in front of it and it's going to solve all the problems. Caching is damn hard. I've been doing this for about 35 years. The number of times when somebody has said, I'll put a cache in front of it and life is going to be good, the number of times they're wrong is close to 100%. Caching is hard. But if you do understand that you want to have caching, understand eventual consistency. Build systems with version data so that eventually consistent data is your friend. Don't run away from it and say, I need synchronous updates across large numbers of nodes, because that is not a scalable solution. Eventual consistency is your friend if you want to go to scale. Why are these things important for us? Because our tenets were security, durability, availability, great. Predictable low latency at any scale. If we want any scale, we need to understand eventual consistency ourselves. Everybody good so far? I've talked a lot about caching. I've talked a lot about the things we do on a request router. What are the things we cache? You want to connect to DynamoDB and make a request. We cache your identity credentials. You want to make a request on some particular table. We cache your table metadata. Suppose you were to make a new connection to DynamoDB on every request. You're probably going to a new request router. Are you going to get the benefit of caching? No. Make sure you have a long-lived connection. What does that mean? Right-size your connection pool. If you have low traffic, have a small connection pool. If you have high traffic, it's okay to have a larger connection pool. If you have a very small amount of traffic, don't have a huge number of hosts who are serving you that traffic. Think about these kinds of things to make sure that you get predictable low latency. Also, if you want predictable low latency from your application, hedge your requests. Send 2 requests. If they're writes, make sure they're idempotent. If they're reads, eventually consistent reads. Choose the first one. Don't change the timeout. And if you're building caches, please, by all means, build constant work into your plan. The other thing which we did in order to give you predictable low latency is this whole concept of limits in DynamoDB. And there's numerous limits we have here. I'm going to talk quickly about a couple of these. There's read and write limits. The motivation for all of the limits we have is predictable latency, because at the end of the day, DynamoDB is running on physical hardware. Physical hardware has limitations. And this hardware is shared infrastructure. We have to make sure that we operate a service which is cost-effective to us so we can translate those benefits over to you. So at the end of the day, we've got physical hardware with some limitations on it. If you created a table, and that table had some number of provisioned RCUs, in the old days, this is historical, we would divide that table into some number of partitions. When we split that table, unfortunately, we divided the provisioning onto those two partitions. This was called IOPS dilution. The reason we have this up here is there's a bunch of people who've been using DynamoDB for a long time who think this is still a problem. This is no longer a problem. The way things work today, if you've got a number of partitions and we split a table, when we split the partitions, each partition gets the same partition level limit. Currently, the limits are 1,000 WCUs and 3,000 RCUs. The numbers may change over time. Don't take a commitment on those. But we have those because we want to guarantee predictable latency. I will make one small detour here. A lot of customers ask me, what is the partition count on my table? This is a meaningless metric for you to ask us. And the reason is simply this. If you were to have a table, there's no guarantee that each table has the same fraction of the key range. Each partition has the same fraction of the key range. The real question you're asking is, I have a big Cyber Monday sale in a couple of days. Is my table going to be able to serve my traffic? The question you need to ask us is this. If I have a different size for each partition, I just made up these numbers here, which partition is going to throttle me first? The real question is, that partition there is the one which is going to throttle you. So just telling you that you happen to have 8 partitions is going to do nothing for you, because 8 times 3,000 or 8,000, 1,000 is useless to you. So we introduced this feature, which was partition table warm throughput, to answer this exact question. I have a major event coming up. Is my table going to be able to serve my traffic or not? So warm throughput is a feature which we launched. We launched it last year at reInvent. Describe a table. It will tell you what the traffic is that you can serve without throttling. Similar limit which we have, transaction size limit. When we launched DynamoDB, a transaction could have no more than 25 items. Today we have 100. We offer standard ACID transactions. If you built stuff with a relational database, we have the same transactions for you. It allows you to build banking applications. All of the guarantees which you want. But our transactions are different. We have 2 kinds of transactions. We have read-only transactions and writable transactions. All of the items in the transaction are specified at one time. All of these things are things which we did because we want predictable low latency. Have you ever been in a situation where your application is hung because somebody started a transaction and went to coffee? Cannot happen in DynamoDB because the transaction contains all of the changes which are going to happen in one place. We offer standard serializable isolation. If you built applications with relational databases, you understand this. We use the standard 2-phase commit approach. Standard 2-phase commit, prepare, commit. Everything is standard the way in which you would expect with a 2-phase commit transaction. We do those things. We did do one optimization for reads. We do not do 2-phase commit for reads because it's cheaper for us to just do the read 2 times. If the items didn't change, your transaction is good. The question is then, why do we have transaction limits? Why 25? Why 100? And the simple answer is this. We want predictable low latency. We did a bunch of testing and we said, if we increase the number of items in a transaction, what happens to latency? and what happens to availability. If you have contention on your items which are being modified in the transaction, availability goes down, latency goes up. When we launched, we were able to safely do 25. Today, we're able to do 100. We want to increase the number even further. These are some of the reasons why we have limits on transactions. Similarly, item size limits. Why do you have an item size limit of 400 kilobytes? Well, it's shared infrastructure. We want to make sure that you do not impact your own usage on some other item which is in the same partition. As the size of the item goes up, the number of times you can read or write that goes down. The number of times, the amount of time it takes is going to go up. We have item size limits of 400K for a limit. If you do need a larger number, I'd love to talk to you about it. We have limits on GSIs, global secondary indexes. When we launched, it was 5. Today, the number is 20. The reason is we want predictable low latency. Am I going backwards or forwards? I have no idea. Okay, today it's 20. We were able to make changes to the software so that we gave you consistent, predictable replication lag to the GSIs. Today the number is 20. Why do you have GSIs? Because you have alternate access patterns. Now, of course, if you have a need for more than 20 GSIs, that's my email address. Please do contact me because I think there's a different conversation we need to have about your schema. Many of these decisions we took, every one of the limits, were to give you predictable low latency because I think that's the one thing which differentiates us from any other database. Predictable low latency at any scale. So I'm going to kind of, I came to the end of this, pretty good. So conclusion is, we talked about the tenets. Every one of the decisions we make as a team is based on our tenets. These are our high-level tenets. Whenever we have a project, whenever we have a new feature, whenever we have a new thing which we want to develop, one of the things which we ask the team is, what are your tenets? Because those are the things which help distribute decision-making across the team, and they make sure that the teams are able to iterate faster. But as a service, these are our tenets. If you ever have a question why we did something, the answer is probably one of these 4. Why did you not store your data unencrypted on disk? Because it'll be faster. First one up there. Why don't we give you some other write guarantee other than we will write to 2 availability zones and it'll be faster, won't it? Durability. We are a regional service. We guarantee that if a complete availability zone were to go away, we will not be in the least bit impacted. Your data is written to 2 AZs before we commit it to you. Availability is our third guarantee. There's no point having availability with wrong data or giving your data to the wrong person. Security, durability, then availability, and to us, as a service, predictable low latency. So my ask to you would be this. In the projects you're building, with DynamoDB, without DynamoDB, it doesn't matter. Think about these things. What are your tenets? How do you drive decision-making in your organization? This is how we drive it in ours. So I hope this was useful to you. We're going to hang around here and answer any questions. But apparently, if you want a hoodie, you have to come and talk to somebody in the database booth. There's no QR code here. There's a whole bunch of trainings which we do offer. The one other ask I have of you is this. Is this. We do these presentations because we believe it's really important to share with you the things which we have learned operating a service at scale and making the choices which we made and learning from you. A part of it is standing here and talking to you about these things, but a part of it is listening to you after these conversations. But if you want more content like this at re:Invent, please do fill the feedback sessions. Thank you very much. I think that's the last one.